So we're all in the correct room. That's good. We're going to talk today about topologies for cost-saving autoscaling. And just to get you prepared, it's not going to be like I'm showing you, this is how you're going to autoscale your environment, but rather ways to think about autoscaling and what are the pitfalls in the architecture of OpenSearch that limit autoscaling in reality. And to kick us off, I'm going to start talking about storing objects, actual objects, ice core samples. If you're unfamiliar, ice core samples are drilled, or these cylinders drilled from ice sheets or glaciers, and they provide us a record of Earth's climate and environment. The interesting thing, I believe, and relevant to us in these ice core samples is that when they arrive at the storage facility, they are parsed. And if you think about it, this is probably the most columnar data of any columnar data that we have. It's a literal column. And it's sorted by timestamp, right? You have the new ice at the top and the old ice at the bottom. And the way the scientific community has decided to parse this data is in the middle of the slide. And it's very clear to them that this is how they want it parsed. And this person managing the storage facility is going to parse the data that way, all of it. And because the scientific community has a very narrow span of inquiry regarding this type of data, it is easy to store it. It is easy to make it very compact. And you can see the storage facility is kind of boring. It's shelves, everything's kind of condensed. A visitor arriving at the facility has an easy time looking for things. It's very well sorted and structured. If we take a hypothetical example of lots of visitors coming, and the person here who is managing the storage facility wants to scale out. He wants to be able to accommodate many more visitors at a time. What he'll do is he'll take all those ice core samples. This is totally hypothetical. Please don't be offended if you're in this field, and cut them in half. Okay, so that's just time divided by 2. That's easy. And add a room, put everything in all these halves in another room, and you can kind of spread out the load. The read load will kind of be spread it out. And it really makes things easy. It's practically easy to think about how you would scale out such a facility. Let's talk about a different object storage facility, like a museum, where we don't really know what kind of samples are coming in. If you have a new sample coming in, it could be a statue, it could be an archaeological artifact, it could be a postmodern sculpture of the Kraken or dinosaur bones. How do we index these things in a way that they're easy to search? It's very hard. One of the things that's interesting is that a visitor at a museum has such a wide span of inquiry. Like, what are they going to ask you? What a person managing the museum, how does he index things so that they're easily queryable? What if someone wants the top K objects in the museum? He'll need these 2, but they're from completely different fields. So when your objects are unstructured, it's very hard to store them in a way that is scalable. If we wanted to scale our museum for this hypothetical situation where many visitors are coming, it's kind of hard to do. Would we have to take half of this dinosaur skeleton and put it in another room? Would we take samples from each exhibit and make a smaller museum on the side? How do you do this? And in some real world cases, there's a lot of visitors who want to see a specific art piece, and it's hard. How do you scale the Mona Lisa? You cannot. It's just there, and everybody's going to wait in line and complain about it later. Similarly to OpenSearch, you can scale it. That's adding nodes. It's a mechanical thing. You're just going to add some machines. But spreading the load when your data is unstructured is difficult. It's not a straightforward answer. And this is why in this particular type of system, and in Elasticsearch as well, you don't have auto-scaling native to the software. So this is me. I'm Amitai Stern. I'm a member of the technical steering committee of the OpenSearch Software Foundation, leading the OpenSearch software. I'm a tech lead at Logs.io, and I manage the telemetry storage team, where we manage petabytes of logs and traces and many terabytes of monitoring and metric data for customers. Our metrics are on Thanos clusters, and everything else that I mentioned, logs and traces, are all going to be stored on OpenSearch clusters. What is OpenSearch? Probably most of you know, but just to get us oriented if you're in the room and you're not really familiar, OpenSearch is a fork of Elasticsearch. So it's very similar. It's been a fork for the last 3 years, and the divergence is not too great. So if you're familiar with Elasticsearch, this is very much relevant as well. OpenSearch is used to bring order to unstructured data at scale. It's the last line over here. So as I said, it is a fork of Elasticsearch. Elasticsearch used to be open source. It provided an open source version, and then later they stopped doing that. OpenSearch is a fork that was primarily driven by AWS, and today it's completely donated to the Linux Foundation. It's totally out of their hands at this point. OpenSearch clusters are monolithic applications. You could have it on one node, and from here on in the talk, this rounded rectangle will represent a node. A node in OpenSearch can have many roles. So you can have just one, and it'll act as its own little cluster. But you could also have many, and they'll interact together. And that's what monolithic applications are. Usually, in the wild, we'll see clusters divided into 3 different groups of these roles. The first one would be a cluster manager. So the cluster manager nodes are managing the state, where indexes are, creating and deleting indexes. There's coordinating nodes, and they're in charge of the HTTP requests. So they're kind of like the load balancer for the cluster. And then there's the data nodes. And this is the part that we're going to want to scale. Normally, this is where the data is. The data is stored within a construct called an index. This index contains both the data and the inverted index that makes search fast and efficient. These indices are split up, divided between the data nodes in a construct called a shard. Shards go from 0 to n. And a shard is, in fact, a Lucene index, just to make things a little bit confusing. So you already used the term index, so you don't need to remember that. But they're like little Lucene databases. On the data nodes are 3 types of pressure if you're managing one. Okay, so you're managing your cluster. You have the read pressure, all the requests coming in to pull data out as efficiently as possible and quickly as possible, and this write pressure of all these documents coming in. There's the third pressure when you're managing a cluster, which is the financial one. Since if your read and writes are fairly low, you'll get a question from your management or from the CFO, like, what's going on? These things cost a lot of money. All this disk space, all the memory and CPU cores. So it's 3 types of pressure. And let's move on to like, why would you even autoscale? So yes, financially, cluster costs a lot of money. We want to reduce the amount of nodes that we have. But what if we just had enough to handle the scale? Okay, so this blue line will be the load. And let's imagine that, and the red line is the load that we can accommodate for with the current configuration. Kind of leave it vague that way. Over-provisioned is blue, and under-provisioned is like the red over there. If we said the max load is going to be X, and we're just going to say, okay, we should just provision for there, and we'll have that many nodes. The problem would be that we're wasting money. And this is good in some cases if you have the money to spend, but normally we're going to try and reduce that. So you opt for manual scaling, and manual scaling is the worst of both worlds. You wait too long to scale up because something's happening to the system, it's bad performance. You scale up, then you're afraid to scale down at this point because a second ago people were complaining, so you're going to wait too long to scale down. It's really the worst. And autoscaling is following that curve automatically. So that's what we want. This is the holy grail, some line that sort of follows the load. When we're scaling OpenSearch, we're scaling hardware. So you have to think about these 3 things, these 3 elements that we're scaling. We're going to scale disk, we're going to scale memory, we're going to scale CPU cores. These are the 3 things we want to scale. The load splits off into these 3. Read load doesn't really affect the disk. So you can have a lot of read load or less read load. It doesn't mean you're going to add disk. So for the sake of this talk, we're going to focus more on the write load and its effects on the cluster because it affects all 3 of these components. And if there's a lot of writes, we might need to add more disk. Or we might need more CPU cores because the type of writing is a little more complex, or we need more memory. I have exactly one slide devoted to vertical scaling because when I was going over this over the talk with other folks, they said, what about vertical scaling? Amazon, behind the scenes, when they're running your serverless platform, they're going to vertically scale it first. And if you have your own data center, it could be kind of easy to do that relatively. Amazon do this because they have the capability to vertically scale easily. If you're using a cloud, it's harder. So when you scale up, usually you go from one set of machines to the next scale of machines. It means you have to stop that machine and move data. And that's not something that's easily done normally. So vertically scaling, for most intent purposes, most companies, is really just the disk. That is easy. And you can increase the number of EBS instances, and you can increase the disk over there. Horizontal scaling is the thing you need to know how to do. If you're managing and maintaining clusters, you have to know how to do this. And OpenSearch, you just have to add a node, and it gets discovered by the cluster, and it's there. So practically, it's easy. And there's a need to do this because of the load, the changing load. There's an expectation, however, that when you add a node, the load will just distribute. And this is the case in a lot of different projects. Here, similar to the example with the museum, it's not the case. You have to learn how the load is spread out. You have to actually change that as well. How you're maintaining the data, you have to change that as you are adding nodes. If the load is disproportionately hitting one of the nodes, we call that a hotspot. Any of you familiar with what hotspots are already? Okay, yeah, many. So you get a lot of load on one of those nodes, and then writes start to lag. So hotspots are a thing we want to avoid. Which moves us into another place of, like, how do we actually distribute this data so it's kind of going to all these nodes in the same fashion, and we're not getting these hotspots. When we index data into OpenSearch, each document gets its own ID. And that ID is going to be hashed, and then we're going to do a mod of n being the number of shards. So in this example, the mod is something that ends with 45, and mod 4 because we have 4 shards. And that would be equal to 1, so it's going to go to shard number 1. So if you have thousands of documents coming in, each with their own unique ID, then they're going to go to these different shards, and it more or less balances out. It works in reality. If we wanted to have the capability to just add a shard, make the index just slightly bigger, why can't we do that? And the reason is this hash mod n. If we were to potentially add another shard, our document is now stored in shard number 1, and we wanted to scale up, so we extended the index just a bit. The next time we want to search for that ID, we're going to do hash mod to see where it is. N just changed. It's 5 and not 4. So we're looking for the document in a different shard, and it is now gone. So that's why we have a fixed number of shards in our indices, and we actually can't change that. So when you're scaling OpenSearch, you have to know this. You can't just add shards to the index. You have to do something we call a rollover. So you take the index that you're writing to, and you add a new index with the same aliases. So you're still writing. You're going to start writing to the new alias, the new index atomically. And this new index would have more shards. That's the only way to really increase throughput. Another thing that's frustrating when you're trying to horizontally scale a cluster is that there's shared resources. Each of our data nodes is getting hit with all these requests to pull data out, and at the same time to put data in. So if you have a really heavy query with a leading wildcard, regex, something like that, hitting one or two of your nodes, the write throughput's going to be impacted, and you're going to start lagging in your writes. And why is this important to note? Because autoscaling, often we look at the CPU and we say, oh, CPU high, add nodes. But that could be because of one of these two pressures. It could be the write pressure or the read. If it's the read, it could be momentary. And you just wasted money by adding a lot of nodes. So on the one hand, we shouldn't look at the CPU, and we might want to look at the write load and the read load. On the other hand, write load and read load could be fine. But you have so many shards packed in each one of your nodes because you've been doing all these rollover tasks that you get out of memory. So these kind of, this is, I'm just trying to give you the feeling of why it's actually very hard to do this thing where you're kind of saying, this metric says scale up. The good news is it's sometimes really simple. And it does come at a cost, similarly to eating cake, but it is still simple. If the load is imbalanced on one of those three different types, disk, memory, or CPU, we could add extra nodes, and it will balance out, especially if it's disk. And similarly, if the load is low on all three, it can't be just one, on all three of those, so low memory, low CPU, low disk, we can remove nodes. And that's when it is simple, when you can clearly see the picture is over-provisioned or under-provisioned. And I want to devote the rest of the talk to when it's actually complicated, because the easy is really easy. Let's assume that we're looking at one of those spikes, right? The load goes up and down, and let's say we want to say that when we see a lot of writes coming in, we want to roll over, okay? And when they go down, we want to roll over again, because we don't want to waste money. So the red is going to say that the writes are too high. So we're going to roll over. And then we add this extra node, and so everything's OK. Then the writes start to go down. We're wasting money at this point. There's 20% load on each of these nodes. If we remove a node, we get a hotspot, because now we just created a situation where 40% is hitting one node, a disproportionate amount of pressure on one. And that's bad. So what do? Do another rollover task, and now it's 25% to each node. And we could do this again and again on each of these. If it's like a day-night load, you'd have way too many shards already in your cluster, and you'd start hitting out of memory. Getting rid of those extra shards is practically hard. You have to find a way to either do it slowly by changing to size-based retention, or you can do merging of indexes, which you can do, but it's very slow. And it takes a lot of CPU. There is a way, rather simple way, to overcome this problem, and that is to overshard. So rather than have shards spread out one per node, I could have 3 shards per node. And then when I want to scale, I'll add nodes and let those shards spread out. The shard's going to take up as much compute power as it can from those new nodes. So kind of like hulking out. That's the concept. However, finding the sweet spot between oversharding and undersharding becomes hard. And it's difficult to calculate. And in many cases, you'd want to sort of roll over again into an even bigger index. So I'm going to suggest a few topologies for scaling in a way that allows us to really maintain this kind of sweet spot between way too many, way too few shards. The first kind is what I'd call a burst index. So as I mentioned earlier, each index has a write alias, and that's where you're going to atomically be writing. You can change this alias, and it'll switch over to whatever index you point to. So it's an important concept to be familiar with if you're managing a cluster. What we're suggesting is to have these burst indices prepared in case you want to scale out. So you don't have to, they can be maintained for weeks, and they will be that place where you direct traffic when you need to have a lot of it directed there. So that's what we would do. We just change the right alias to the right data stream. And that would look something like this. There's an arbitrary tag, a label we can give nodes called box type. You could tell an index to allocate its shards on a specific box type or a few different box types. So the concept is you have burst type, the box type burst, and you have box type low. And as long as you have low throughput in your writes, and again, that is probably the best indicator of I need more nodes, is the write throughput. So if we have a lot of writes, a low throughput on the writes, we don't need our extra nodes. And the low write throughput index is allocated to indexes that have the low box type. If throughout the day the throughput is not so low and we anticipate that we're going to have a spike, and this again, it's so tailored to your use case that I can't tell you exactly what that is. But if you see, in many cases it is that the write throughput is growing on a trend, then what you do is you add these extra nodes. And you don't need to add nodes that are as expensive as the other ones. Why? Because you don't intend to have that amount of disk space used on them. They're temporary. You can have a real small and efficient disk there on these new box types. So you create the new ones. The allocation of our burst index says it can be on either low or burst or both. And all you have to do is tell that index that you're allowed to have total shards per node 1. And then it automatically will spread out to all of these nodes. At this point, you're prepared for the higher throughput, and the write alias, you switch the write alias to be the high throughput index. So this is the burst index type. As it goes down, you can move the shards back by doing something called exclude of the nodes. You just exclude these nodes and shards just fly off of it to other nodes. And then you remove them. So this is the first form of auto-scaling. It works when you don't have many tenants on your cluster. So if you have one big index and it may grow or shrink, this makes sense. However, in some cases, we have many, many tenants, and they're doing many different things all at the same time. Some throughputs spike, and others will kind of go down, and you don't want to be in a situation where you're having your cluster tailored just for the highest tenant, the highest throughput tenant, because then again, you are wasting resources. Which brings me to the second and last topology that I want to discuss here, which is called the burst cluster. It is very similar to the previous one, but the difference is kind of big. We're not just changing the index that we're going to within the cluster, we're changing the direction to a completely different cluster. So we wouldn't be using the write alias, we would be diverting traffic. And it would look something like this. If each of these circles is a cluster, and each of them have that many nodes, why would we have a 10 and a 5 and a 60? The reason is we'd want to avoid hotspots. So you should fine-tune your clusters initially for your average load. The average load for a low throughput might be 5 nodes, so you want only 5 shards. And for a higher throughput, you want a 10-node cluster, so you have 10 shards each. If you're suffering from hotspots, all you have to do to fix that is spread the shards perfectly on the cluster. And that means 0 hotspots. So in this situation, we've tailored our system so that on these green clusters, the smaller circles, they're fine-tuned for the exact amount of writes that we're getting. But then one of our tenants spikes while the others don't. We move only that tenant to send all their data. We divert it to the 60-node cluster, capable of handling very high throughputs, but not capable of handling a lot of disk space. So it's not as expensive as 6 times these 10-node clusters, but it is still more expensive. So data is being diverted to a totally different environment. We use something called cross-cluster search in order to search on both. So from the perspective of the person running the search, nothing has changed at any point. It's completely transparent for them. And in terms of the throughput, nothing has changed. Like they're sending much more data, but they don't get any lag, whoever's sending it. And all the other tenants don't feel it. There are many more tenants on this 10-node cluster, and they're just living, their best life over there. You could also have a few tenants sending to this 60-node cluster. You just have to manage how much disk you're expecting to fill at that time of the burst. A way to make this a little more economical is to have one of your highest throughput tenants always on the 60-node cluster. So you still maintain a reason to have them up when there's no high throughput tenants on these other clusters. And this is a way to have this is a way to think of auto-scaling in a way that is a bit outside of the box and not just adding nodes to a single cluster. It is very useful, by the way, if you are running a feature that is not very used in OpenSearch, but is up and coming, called searchable snapshots. So if you're running searchable snapshots, all your data is going to be on S3, and you're only going to have metadata on your cluster. The more nodes you have that are searching S3, the better. So they can be small nodes with very small disk, and they could be searching many terabytes on S3. But if you have one node with a lot of disk trying to do that, the throughput's going to be too low and your search is going to be too slow. So if you want to utilize these kind of features where your data is remote, you have to have many, many nodes. So that's another reason to have such a cluster just up and running all the time. You could use it to search audit data that spans back many years. Of course, we don't want to keep it there forever. A way to do that is just snapshot it to S3. Snapshots in OpenSearch are a really powerful tool. They're not the same as they are in other databases. It takes the index kind of as it is. It doesn't do any additional compression, but it stores it in a very special way, so it's easy to extract it and restore cluster in case of a disaster. So we would move the data to S3 and then restore it back into these original clusters that we had previously been running our tenants on. And then we could do a merge task. Down the line, when the load is low, we could merge that data into smaller and smaller indexes if we like. Another thing that happens usually in these kinds of situations is that you have retention. And once the retention is gone, just delete the data, which is great. Especially if you're in Europe, you have to delete it like right on time. So this is the burst cluster topology. I like to summarize. It's going to be a bit long. That's why it's happening at this point in time. So just to summarize, there are 3 different resources that we want to be scaling. Okay, you have to be mindful when you're maintaining your cluster, which one is the one that causes the pressure. Okay, so if you have very long retention, then disk space. And you have to start considering things like searchable snapshots, or maintaining maybe a cross-cluster search where you have just data sitting on a separate cluster that's just accumulating, in very large disks, whereas your write load is on a smaller cluster. So that's one possibility. If it's memory or CPU, then you would definitely have to add stronger machines. So we have to think about these things ahead of time. Some of them are a one-way door. So if you're using AWS and you add to your disk space, in some cases, you may find it difficult to reduce the disk space again. Okay, this is a common problem. And when I say that, the main reason it is because when you want to reduce a node, you have to shift the data to the other nodes. And in certain cases, especially after you've added a lot of disk, that can take a lot of time. So some of them are sort of a one-way door. And many of them require a restart of a node, which is potential downtime. We talked about these 2 topologies. I'll remind you, the burst index and the burst cluster, which are very important to think about as completely different options. And I like to highlight that first option that I gave, sort of the hulking out, like the over-index, the over-sharding proposition, is also viable for many use cases. If you have a really easy trend that you can follow, if your data is just going up and down and it's the same, 12 at noon, people are sending, 2x. Midnight, it goes down to half of that, and it keeps going up and down. By all means, have a cluster that has, 10 nodes with 20 shards on it. And when you hit that afternoon peak, just scale out and let it spread out. And then when it gets to the evening, then scale down again. If that's your use case, you shouldn't be implementing things that are this complex. And you should definitely use the concept of oversharding, which is well known. I like to talk about some upcoming key features, which is different than when I started writing this presentation. These things changed like in the last month or so. The OpenSearch Software Foundation, which supports OpenSearch, One of the things that's really neat is that from it being very AWS-centric, it has become much more widespread. So there's a lot of people from Uber and Slack, Intel, Airbnb, developers starting to take an interest and developing things within the ecosystem. They're changing it in ways that will benefit their business. And if that business is as big as Uber, then the changes are profound. One of the changes that really affects autoscaling is read-write separation. And that's going to come in the next few versions. I think it's nearly beta, but a lot of the code's already there. I think this was in August when I took this screenshot, and it was 5 out of 11 tasks. So they're pretty much there by now. This will allow you to have nodes that are tailored for write and nodes that are tailored for read, and then you're scaling the write and you're scaling the read separately, which makes life so much more simple. Yeah. Woo. All right, and the other thing, it's not me right now, so, okay. The other one, which is really cool, is streaming ingestion. So one of the things that really makes it difficult to ingest a lot of data all at once is that today, in both Elasticsearch and OpenSearch, we're pushing it in. And the index is trying to do that, trying to push the data, ingest it, but the node might be overloaded, in which case the shard will just say, I'm sorry, CPU up to here, and you get what is called a write queue. And once that write queue starts to build, someone's going to be woken up, normally. If you're running, let's say, observability data, that's a wake-up call. In pull-based, what you get is the shard is hard-coded to listen and retrieve documents from a particular partition in, for example, Kafka. It would be pluggable, so it's not only Kafka. But let's just, since it's very common, let's talk and use Kafka as an example. So each shard will read from a particular partition. A topic would represent, let's say, a tenant. You could have a shard reading from different partitions from different topics, but per topic it would be one. So shard 0 from partition 0, etc. What this gives us is the capability for the shard to read as fast as it can, which means that you don't get the situation of a write queue because it's reading just as fast as it possibly can, based on the machine, wherever you put it. So if you want to scale, in this case, it's easy. You look at the lag in Kafka. You don't look at these metrics in terms of like the cluster. The metrics here are much easier. Is there lag in Kafka? Yes. I need to scale. Much easier. Let's look at CPU, let's look at memory, let's see if the shards are balanced. It's much harder to do. And in this case, it'll make life much, much easier. That is my talk. Open for Q&A if anybody has any questions. Okay. Thanks. Yeah.
Hi. I had a question about that last thing you talked about streaming ingestion. Beyond just looking at a metric, at the lag in Kafka, does that expose a way to know precisely up to which point in the stream this got in the document? We use OpenSearch in a bunch of places where we need to know exactly what's available in the index so that we can propagate things to other systems.
So at this, I don't know if you saw, it is an RFC. It's a request for comments.
Okay, so there's not a feature yet.
Right now, it's in the phase of what we call like a feature branch, where it's being implemented in a way that it's like totally breakable, and we're not going to put that in production. But if you have any comments like that, please do comment in the GitHub, so you can come up and I'll share a link. That would be welcome. Yeah, it's in the exact phase where we need those comments. Yeah.
So might be a slightly off-topic question.
Sure.
So this is time series data, right? Do you also roll your indexes by time, like quarterly or monthly? Or how do you combine this approach with burst indexes with situation where you have indexes by...
If it's retention-based.
Along the time axis.
So one of the things you can do is you have the burst index. You don't want it to be there for too long, right? That's the question? Like the burst index, you want it to live longer than the retention, if I understood correctly.
It's not just the burst indexes. Your normal indexes
Oh.
are
So
separated by time.
in some cases, if your indexes are time-based and you're rolling over every day, then you're going to have a problem of too many shards if you don't fill them up enough. You'll have basically like shards that have 2 megabytes inside them, and like it just inflates too much. If you have 365 days or 2 years of data, that becomes too many shards. So I do recommend moving to size-based, like a hybrid solution of size-based, as long as it's less than X amount of days, so that you're not exactly on the date, but better. Having said that, the idea is that you have your write alias pointed at the head, okay? And then after a certain amount of time, you do a rollover task. The burst index, you don't roll over necessarily. And that one, what you do instead of rolling over, you merge. Or you do a re-index of that data into the other one. And you can do that. It just takes a lot of time to do, but you can do that in the background. Yeah, I didn't go into like, there's nitty gritty here, but we didn't go into that, yeah. Sure.
I have two questions. Number one, I think you mentioned reader and separation of reading and writing. It's already supported in OpenSearch serverless in AWS. So am I missing something? The one that you are talking about, is it going to come for the regular OpenSearch and it's not yet implemented?
I don't work at AWS. I'm representing the open source. Both of these are going to be completely in open source. They're not being.
But that's what I'm saying. Like
yeah.
It seems like it's already there in. I forget the version, maybe 2.13, 14, something like that. So you mentioned it is a version that is coming.
Yeah.
But I have practically observed that it's already there. So
you mean in the Amazon
serverless?
Yes. So Amazon serverless is a fork of OpenSearch, and it took a great deal of a nice amount of engineers, more than a year, to kind of separate these two things, these concepts of like OpenSearch as a monolithic application and having the read-write. I can tell you that a lot of these improvements, they're kind of working upstream. They like to add these special capabilities like read-write separation, and then they contribute a lot of the stuff back into the open source. Okay. So you'll have it, in some cases, you'll have features already available in the Amazon OpenSearch offering, and then later it'll get introduced into the OpenSearch open source.
Okay. And the strategies that you explained just now, and they are coming, especially the second one with the Kafka thing. When is it? What version? Is there a plan?
Again, this is very early stage. The pull-based indexing.
Yes.
That one is at a stage where we presented the API that we imagine would be useful for this. We developed the concept of like it'll be pluggable, like which streaming service you'd use, and it's at a request for comment stage. So I present it because I am happy to present these things and ask for comments. So if you have anything that's relevant, just go on GitHub and say, look, we're using it for this, and I don't know, one-to-one doesn't make sense to us. So
okay,
if that's the case, then yeah.
So it can take about 6 months to a year.
We're trying to that particular one. We're trying to get in under a year. I don't think it's possible in 6 months, to be honest. That's a stretch.
About a year.
Yeah.
Okay. Thanks.
Yeah.
I think this question pertains to both the burst index and the burst clustered solution. But if you have a document, I think I understand how this helps for writing new documents. But if you have like an update or a delete operation where you're searching across your old index or your normal index and then either the burst index or the burst cluster, and that update or that delete is reflected in the burst cluster, like how does that get rectified between those two?
One of the things you have to do if you're maintaining these types of indexes, like a burst index, is you would want to have a prefix that signifies that tenant, so that any action you do, like a deletion, you'd say delete based on these aliases. So you have the capability of specifying either the prefix with a star in the end, like a wildcard.
Mm-hmm.
You could also give indexes, and it's very common to do this, especially if it's time series data, by the way, is to give a read alias per day. So you have an index, and it contains different dates with the tenant ID connected to them. So when you perform a search, that tenant ID plus November, what is today, the 17th or 18th? Then it'll search. That index is then made available for search. You can do the same thing when you're doing operations like get for a delete. You can say, these aliases, I want to delete them, or I want to delete documents from them. And it can go either to the burst cluster, or you could go to the indexes that have completely different names, as long as the alias points to the correct one. The cluster means you have to really manage it. You have to have some place where you're saying, this tenant has data here and there.
Mm-hmm.
And the date that I changed the tenant to be over there and the date that I changed them back. It's very important to keep track of those things. I wouldn't do it within OpenSearch. It's a common mistake when you're managing OpenSearch is to say, I have OpenSearch, so I'm going to just store lots of information in it, not just the data that I built the cluster for.
Mm-hmm.
You really should it should be a cluster for a thing and not for other things. So audit data should be separated from, let's say, your observability data. You don't want to put them in the same place.
Thank you.
Sure.
Great talk, by the way.
Thanks.
Yeah. So a question regarding the burst clusters as well as the burst nodes that you have. With clusters, how do you redirect the read load directly? Like, are you, is the assumption that we do like cross-cluster search where
Yes.
you have with OpenSearch dashboards in particular, when you have all your alerts and all that, and with observability data, you are querying a particular set of indexes. So when you move the data around clusters, how do you manage the search? Would be the question.
Okay, so a few things. For alerting,
yeah,
it is very difficult to do this if you're managing alerting using just the index. If you use like a prefix, it could work.
yeah,
When you search if you're doing cross-cluster search, the way that feature works is that you provide, in the cluster settings, you provide the clusters that it can also search on.
yes,
Okay. And then when you run a search, if you're doing it through Amazon service, it should be seamless. If you're running it on your own, you do have to specify, instead of just search this index, it doesn't know that it has to go to the other cluster. You have to say, within this cluster and that cluster and the other cluster, search for this index. So there is a multiplication of, like, you kind of have to add these extra indexes to your search. Yeah.
Understood. Yeah, there's a colon kind of mechanism where you put in. So basically,
Yeah.
what you're expecting here is an addition to write. With read, we have to keep that in mind before spinning up a burst cluster.
Yeah, you have to keep track where your data is
Yeah,
when
okay.
you're moving it.
Got it.
Yeah.
So the second part of the question with burst nodes is, so I'm assuming you're amortizing the cost of rebalancing, because whenever the node goes up and down, so your cluster capacity or the CPU, because shards are moving around, and that requires CPU, network storage, the transport actions are happening. So you're assuming as part of your capacity planning, you have to amortize that cost as well.
Yes, moving a shard while it's being written to,
Yeah.
and it has already 100 gigs on it, moving that shard is a task that is just going to take time.
Yeah.
You need high throughput now. So it's kind of amortized, but it's very common to do a rollover task with more shards when your throughput is big. So it's kind of the same. Like, you'd anyway be doing this. You'd anyway be adding you'd anyway be rolling over to an index that has more shards and more capability of writing on more nodes. So it's sort of amortized, but
Got it. I mean, with
Depends
the
how you look at it.
rollover, you're not moving the data though, right? Like, it's new
Yeah.
shards getting created.
we don't want to move data when we're doing the spread out. That really
Yes.
slows things down.
Got it.
Yes.
Thank you.
All right. Thank you very much for coming, and have a good one.